Hello, let's do evolutionary paleoecology. Yeah, interesting subject. You could see this as the study of evolution of biological organization. And so, what does that mean? Just think about it. Imagine as you go through the day, all of the different biological entities, species, for example, that you've interacted with. Break down your breakfast, your lunch, your dinner. How many different species go into that you know of? Then think about the trees that are putting out all kinds of pollen that's making it hard to breathe right now, and all the different plants that are blooming. The plants that you put the flower vase you've got, the plants you watered, on your windowsill. Think of all the bacteria that are colonizing us and are inside of our gut. They vastly outnumber the actual eukaryotic cells in our body. Think of all of the disease-causing organisms that we're, sort of swimming around in all the time. Hopefully, not getting too sick. Hopefully, our immune system takes care of it. This is all part of our ecology in a way. And now imagine this for animals in their actual environment. It's trying to figure out how things end up organized the way they are. And obviously there's nobody out there, like, no, 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 you go over here, you go over there, organizing in that way. But you do tend to get ecosystems with particular organisms occupying particular roles. And so, it's the macroevolutionary consequences of ecological roles and strategies. Yeah, basically everybody's trying to survive, but uh, in doing so, they're going to bump into a bunch of other species that are also trying to do the same thing. And it's the study of how those interactions occur. And there are people that are much better at this than I am, and they're right here at this university. And so go talk to them if you want to know more. We're going to focus on paleoecology because I feel so much better when we're talking about fossils. Um, what we've got over here is the famous Sepkoski curve, named after J. John Sepkoski, who basically dedicated his life to cataloging every single fossil, figuring out if the name was valid, figuring out when it was first found, when it was last found, making lists, analyzing them, updating those lists. A lot of this is before there were really good spreadsheets like we would use now. Winter 1993. Yeah, there was not spreadsheets then were not like spreadsheets now. Yeah, you were doing a spreadsheet on your IBM compatible, that was 80% compatible computer, or your souped up Commodore 64, something like that, maybe. Yeah, very different time. Past punch cards, but not that far past. So anyway, what he has done is to catalog the number of different types of organisms that existed over time. And this is the best way to see what are the consequences of evolution? What types of animals live at the same time in the same place? Yeah. How does ecology work? When there's an extinction event, which animals are more affected than others? He's only dealing with animals. There are separate people that would try to do this with plants, but yeah, forget about them. We're going to focus on the animals. And what he identifies are particular fauna. And you may have noticed something like this. Like when we're at a Paleozoic site, we're going to find a whole bunch of crinoids. We're going to find tons of brachiopods. But if you go to a site that's just a little bit after this, let's say a nice Cretaceous site up by Fort Worth, you're going to find lots of echinoderms, tons and tons of bivalves and gastropods, hardly any, maybe no brachiopods. You're super lucky if you get any trace of a crinoid whatsoever. And that is the new way. And this won't just be confined to one particular depth. This is going to be a kind of a global change from the top to the bottom of the ocean. You get areas where the old ones hang on, but for the most part, they have been replaced. And so he's dividing it up into three main fauna. These are going to be the Cambrian fauna, which are going to be groups that are going to be rich in trilobites. And what are the things that live around trilobites? So particular kinds of sponges, particular kinds of brachiopods, arthropods, things like that. But yeah, the trilobites will be the defining feature there that'll let you know that's what you're dealing with. We will have Paleozoic fauna, which is going to be very brachiopod rich. That's why we have such a good brachiopod collection, because there are so many different kinds. But also all the things that are living alongside those, things like crinoids, for example. And then we're going to have our modern fauna coming in. And the modern fauna start out slow and then gradually build up speed. And these are going to be the more mollusk-rich fauna. Most of the invertebrates that you would run into would be mollusks. And then echinoderms are still kind of out there all over the place. They're doing pretty well. Think of all the starfish and sand dollars and stuff like that, sea urchins in the world. Yeah. All right. So, of these types, the only type that is actually really and truly extinct are the Cambrian type. And so there were a lot of monoplacophorans. There were eocrinoids, for example. You remember eocrinoids, right? Trilobites, brachiopods, but like mostly lingulid brachiopods at this particular time. And you can still find areas, like you'll get a few lingulids that are surviving today. You don't get any eocrinoids, but you will get crinoids in some places, mostly deep ocean, but yeah. There are a few monoplacophorans, mostly deep ocean. But yeah, the actual fauna of all these things living together and you finding these things together throughout the world, that time has passed. It had its little peak right here in the early Cambrian, and then it goes down, and then it's gone. Yeah. The Paleozoic fauna are going to have a lot of echinoderms in there. You're going to have corals coming up and starting to dominate. Sponges are kind of here all the time. They're not really part of any of these things. They just always are around. But things like cephalopods, yeah, are going to get real big in the Mesozoic in particular. Yeah. Graptolites were very big early on. We'll cover those with the chordates. And then the modern fauna, you're going to have things like fish, modern crustaceans, which there were some of these things that existed in earlier times, but they're not dominant. They're not the main component of the ecosystem usually. And things like mammals and, yeah, bivalves and gastropods being everywhere, which existed during earlier times, but were not in charge during earlier times. So, based on this, Jablonski and Bottier are distinguishing these big changes. So the idea is that in areas that are right near the shore, so you're just in the water, but you're in shallow water, think tide pool, this is the area where we tend to see species originate. So they will appear first close to shore. And this is an area where there is sometimes shelter, where there's a high amount of food because it's very shallow, and so the sunlight can get there, and you can have lots of phytoplankton, for example. And some things never make it out of the tide pool, but others do. And so some of those will then go out into the more competitive sort of offshore area. Lower food density, but if you can move around in particular, then there are greater possibilities for roving around and controlling the environment. And then what happens is that you'll get new things originating onshore, and they will push things into the offshore. That's the only place they can make it now. And then from there, what you'll actually have is the retreat offshore. And so this is going to be the extinction of things close to the shore. And so the most primitive faunas that we have, these things that are basically Paleozoic type faunas with sea stars and brachiopods and stuff like that. You get those in really deep water. You get those around Antarctica. They're just in places where it is very difficult for modern fauna to colonize at present. And I think in the fullness of time, modern fauna will come in and will displace all of these things. Snails will drive everything else to extinction. Snails and like starfish and urchins maybe. But yeah, that's the idea. And so that actually shows up in the fossil record when you look at all the species, all the genera, all the families over time. You can look at the rate that new families form. So this is the origination of uh, new families. Actually, no, it's probably genera. And this is the extinction of some of the genera that were there. So you can see that over time as well. Okay. There are several major extinctions. Each of these is going to get its own separate little mini lecture, or at least most of these are. Yeah, we've got the big one right here, the end Permian extinction. That one came about as close as anything has come to wiping out life. You had the one at the end of the Cretaceous. This is all the dinosaurs dying in a big fireball, and that's fine. Yeah, that's medium size. There's another fairly big one here at the end of the Triassic. There's a quite big one in the Devonian. This is a weird one. We think it may have been caused by plants. Yeah, plants as agents of extinction. And there are extinctions in the Cambrian, which may be more like rapid replacement of organisms by other organisms. Hard to say. And then there's in the Ordovician, basically the world essentially freezes over, and we get this really cold period, and there's a big extinction there as well. Yeah, right after the Great Ordovician Biodiversification Event, which is like the long tail of the Cambrian explosion, is how people describe it. Yeah. All right. So let's talk tiering. We have alluded to, mentioned, said we're going to talk about ecological tiering. Let's talk about it. Let's just talk about it. This is the idea that if you are at a certain height above the sea floor, you are in a different part of the water column. If the water is moving more or less horizontally, there's going to be food flowing past you like this. And so if you go up a little higher, you can then catch that food. You can interdict the current at that particular height. Now, if everything is the same height, then everybody's trying to eat out of the same bowl, and everybody goes hungry, and, Highlander rules, there can be only one, that sort of thing. And so what you see as these species diversify and change, a big thing that they're going to change is going to be their tiering. It's going to be literally how high they stick up at maturity from the floor. Yeah, essentially. So there are some things that are really close to the ground, and some things that are relatively high off the ground. And the idea is that the ecosystem can support more animals when they are ecologically tiered. This is just one way to do it in the water, because each of these animals can then eat, and they can all still survive. So back before there was a lot of motility, ecological tiering was probably a big thing. With motility, potentially you can move to a different place, but in the Paleozoic communities in particular, you see a lot of this, also some of this in the earlier communities, like the Cambrian type communities. But yeah, for different organisms, for things like sponges, they're going to be relatively low to the ground. But corals at this time are going to actually try to elevate themselves a little higher. They'll be a few centimeters up, which potentially gives them a completely different feeding zone. And so on. There are going to be different kinds of corals and bryozoans that are in this range, others that are really tall. And that's fine, because remember, sponges are always pulling water in, and so they can essentially clear out an entire water column at different heights if they are high enough. But you do get some sponges where they actually grow something like a stalk, and then the actual filtering part is raised up off the seafloor. Yeah, quite a bit. And presumably for ecological tiering reasons, you see a lot of those in the deep ocean. All right. Here is the sort of tiering you would see in Paleozoic type fauna. That was in Cambrian type fauna right there. So yeah, you'll have things that are low to the ground. Things like, for example, sea cucumbers and stuff. You'll have edrioasteroids. That's great. This is, I think, just looking at, echinoderms. And then they're saying that, all right, there are other creatures that would be able to stand up. And so some of these early rhombifera were raising themselves up a little bit. They go on to become things like paracrinoids and regular crinoids right over here. And then you'll get some other groups that are actually going to develop very long stalks, particularly crinoids, but also some blastoids and blastozoans, things like blastoids, that are going to specialize in having a really long column. And so you can have 6, 8, 10 feet of stem for one little tiny calyx. And that's putting a lot of energy into development because they have to recruit and spend energy to build each of those little segments. But yeah, the new segments grow right underneath the cup of a crinoid, and so it can just keep elevating itself up there, just building a little tower, one step higher at a time. Yeah. In addition to the epifaunal suspension feeders, there's also an infaunal tiering. There are organisms that exist only in the sort of top part of the sediment. There are some that will burrow further down and have access to a different, essentially nutrient ecosystem down there. And they're going to be, ones that burrow even further than that. Yeah, very peculiarly. And of course, along with this, the other thing that's going to be big in paleoecology is predation. And so here are the fossils with the first evidence of predation. And these, I believe, come from the end of the Ediacaran, I think is when these are from. If not, it's the very early Cambrian. But I believe this is late Precambrian. And these are some of the first animals to have a biomineralized shell. And you can see in this, you got these little drills. Something was just sitting there, probably working really slowly. Maybe it had one or two little teeth, and it was just rotating them around in a circle. Because once it was able to break through, then bam, you get access to the organism inside. And just slurp out the guts. Here are some with evidence of survived attempts at predation. So there was drilling here, and I don't know why the drilling stopped. Maybe the organism just tasted bad. Yeah. But there's evidence of repair from inside where they sort of papered over those holes and regrew it. And there's evidence of what may have been fatal boring attempts. Here's another tube-like organism from the same time. This one doesn't have any boreholes on it, but Claudina, which are these guys, have loads of boreholes in them right from the get-go. So biomineralization is often seen for this reason as a direct response to the rise of predation, or you could look at it as like a Red Queen type situation, which is where there's a constant arms race. It's like, you're predating on me, I'm going to develop a shell. You've developed a shell, I'm going to develop a little boring device that can drill a hole into the shell. You've done that, I'm going to develop some kind of toxin that I'm going to coat the shell in. And you've developed that, I'm going to develop some kind of antitoxin and so on. Or I'm going to develop crushing jaws so I don't even need to bore in there, I can just smash it up. Yeah. That sort of thing. That's Red Queen hypothesis evolution, that you basically run about all the time, constantly developing new things because it's the only way to keep your head. Yeah. So there we go. And that's the end of our little paleoecology taster. Just to show you a little bit of what this is, there's a bunch of pollen up here because that is great for paleoecological records. You get tons of it. It's deposited in ponds, for example, and it fossilizes just beautifully, very identifiable. You can sometimes identify it to which, current extant species it is. And it tells you how well the trees were doing, how well the plants were doing. When was there a big forest fire? What was happening? All this is foreshadowing for some of the extinction lectures to come. So I hope that was interesting as well. Thanks a lot.